Good evening, everybody. My name is Mainak Bhattacharyya. I'm currently a master's student in Department of Physics at NIT Jamshedpur. Today, I'm going to present a paper on a quantum algorithm for signal decoding of classical error correcting linear block codes. The authors of the paper are me, myself, and Dr. Onku Raina from ISL. I'll start with some basics of linear block code. It is basically a classical error correcting technique to deal with the noises that has been implemented by a noisy channel during communication of the message. For example, here we have a data stream that will be sent through a communication channel, and what linear block code does is it divides the entire data stream into little blocks of equal size. For example, here is our data stream that will be transmitted through the communication channel, and it is been divided into little blocks of message bits of number 3. That is, the whole string is been divided into three bits of message of equal size each. And so what we'll do is that the encoding will transform this each block into an encoded code word, which has higher number of bits than the message bits. So these 3 bits will be represented by a row vector that will be operated on a generator matrix specific to a linear block code, and that will generate a code word of higher number of bits that will be represented by nkd. N is the number of bits in the code word, k is the number of bits in the message, and t is the Hamming distance of the code. Now, this D has a significance that this D will signify the error correcting capability of the linear block code. So whether a linear block code can detect and correct the errors of more than one or two, that will be signified by this D. And after we have encoded our code word from the message, we'll go for the decoding process to know what was the actual message that has been sent by the sender to the receiver. And our focus lies on the syndrome decoding process. The syndrome decoding process is basically when the code word has been transferred into the noisy channel, noise will invert some of its bits, obviously, and it will take the code word to an erroneous vector. And when the receiver received an erroneous vector, he or she will apply the parity check matrix transpose. This parity check matrix will also be specific to a linear block code and will be known to us. So applying the erroneous vector to this parity check matrix transpose will give us the syndrome. And having syndrome in our hand and the parity check matrix in our hand, we can solve this equation 2 for a solution. Now, if we elaborate this second equation, we can see that the syndrome doesn't depend on the code word. So solving this will give us the error vector, and the error vector is the minimum solution of it. So the solving equation 2 will give us solution. Now there is multiple solutions, and out of that solution, we are requiring the solution of the minimum weight. And this can be explained further very simply that we are searching among this orange domain, which has 2 to the power number n, and n is the number of bit of code word. So because error can happen in any of those n bits, the total possibility of the error vector is 2 to the power n. Out of that, 2 to the power k satisfies this syndrome because the syndrome doesn't depend on the code word, as I said. So the syndrome will be same for all the code word having been affected by the same error vector, and that will give rise to a solution of 2 to the power k numbers. But out of this 2 to the power k, we're searching for an element in this domain which has the minimum weight. But this process is exhausting, and Berlick in 1978 proved that this searching process is incomplete. That is, for syndrome decoding of classical error correcting linear block codes, there is no algorithm which can solve this problem in polynomial time complexity. And this gives rise to a problem because this is a very exhausting search process. For example, if I can explain this simply, we have a database and we are searching for an element which satisfies certain condition in, suppose, in form of a function satisfying condition. So suppose the element is in the third entry. So we're searching for the first, and as soon as we get in third entry, we have done our searching process because we have the syndrome. But in this case, we are lucky because we get the entry which satisfies the syndrome in third entry. But in our case, this contains a minimization problem. So we get the third entry, we reach the third entry, and we get the we see that the state satisfies the syndrome, but we don't know whether it has a minimum weight. That is, it has a minimum number of ones among all the other entries and satisfies the syndrome. So for that, we have to compare that entry with the other entries also, because there can be other entries which also satisfy the syndrome, but that can have a weight that is less than the third entry. So we have to search through all the 2n possibilities of error vectors to get an answer whether what is the our actually the error vector that has been implemented by the noisy channel. And to have a better time complexity, we have used the quantum parallelism and the Grover's algorithm to have a quadratic speed up in the searching process. The Grover's algorithm can be expressed simply in this manner, that we start with the uniform superposition of all the elements represented in the database of searching. Then we apply the Grover operator for this much optimal number of iterations, and then we measure qubits, and after that we'll get any of the solution states with higher number of probabilities. That is, now, in this case, the optimal number of iteration, this aim is the number of solutions exist. And the amplitude inversion basically marks the solution states. And due to the amplitude inversion, when we do the second step of the Grover algorithm, that is inversion about the mean, the inverted amplitudes will get amplified, and the non-solution states, as their amplitudes haven't been inverted, their amplitudes will get reduced. In this way, we have modified the probability of occurring the solution state at the output. But in our problem, the number of solution states is unknown, because that is our goal, that to search the minimum worst solution, and we initially don't know how many number of error vectors satisfy that certain condition. So initially that is unknown. Now also we need to minimize their weight while searching through the database. So there are two conditions that should be satisfied, and for that, this optimal number of iteration number cannot be known from beforehand. For that, we approximate this number of iterations through this modified covert search. And what we have done, suppose we are searching for the index which satisfies the sigma. Now there can be multiple indexes satisfy this condition. We have to search those solutions. And for that, we need to have a proper number of iteration number. And that proper number of iteration number we have been defined through a parameter L. And we have defined another two parameters to handle the modification of this parameter through the algorithm. So approximating the appropriate number of iterations, and this lambda can be determined between 1 and 4 by 3 as suggested by this paper of Michael Poyer et al. This can be taken between 1 and 4 by 3, but we have taken 6 by 5 just for convenience. Now this is the BBHT loop, which does is that we operate Grover operator say for L equals to 1 time. Then we measure the qubit. If it satisfies this condition, we end the algorithm. Otherwise, we'll update M and L in such a way to again approximate this optimal number of iteration and run the algorithm. Now, as you can see, this algorithm runs for optimal number of iterations less than pi by 4 whatever 2 to the power n. And this is the optimal number of iterations to search for one element in the database. So throughout this algorithm, whenever we stop, that is never exceeding this value, and that gives rise to a quadratic speedup of our searching process. Now, based on the previous modified Roberts algorithm and an algorithm suggested by Dorher, we have suggested a decoding algorithm for our syndrome decoding process. That contains a state initialization of equal superposition of all the 2 to the power n states present in the database. Then we define a minimization parameter for our algorithm, which will help in minimizing the weight for our algorithm. Then we run a minimization loop that will stop until the Oracle number of Oracle queries reaches certain value. That will explain later how that will gain. Say after X number of Oracle queries, we exit the algorithm. And this kind of approach is known as infinite algorithm approach. Now, in this infinite algorithm approach, in first step, we mark all the states having the syndrome S, that is our searching criteria. Also, another criteria is that we have to minimize the weight. So we start from saying that, okay, mark the state which has the syndrome and weight less or equal to the initial parameter. By this way, we do the modified cover search and as seen, and we measure the qubits. Now, as seen from the previous slide, the modified cover search has two outcomes. One, the solution that we are searching for. Otherwise, we run the BBHT loop again and again. And as here also, there are two loops, one for the minimization and one for the criteria satisfaction of the syndrome and weight, that is the BBHT loop. So we'll run the BBHT loop, and if certain state has come as an output which satisfies the syndrome and weight less equal to this initial parameter, we'll jump onto the third step with updating delta, and we update delta by the weight of the solution state that has satisfied this condition. So we're updating delta whenever we are getting this, when getting an output satisfying this condition, by taking the parameter to be the weight of that solution state. But if we don't get a solution, then we don't update delta and we run the modified over search again. The crucial step is that whenever we're running the modified cover search, that is in the second loop, whenever we're running the BBHT loop, we're updating the number of Oracle queries by the L that is here by that value. That is, the modified cover search produces a certain number of Oracle queries at each loop, and we are adding the certain number of Oracle queries at each number of loops that has been going on here. And whenever that value reaches X, it's exiting the infinite algorithm. And that optimum number of iterations we get from the Dorher's paper of the Dorher's paper for the minimization algorithm. That is 22.5 root over 2 That is, after this Oracle queries, we are exiting the algorithm and we're getting the output state with the probability 50%. And this works because here we have chose the initial parameter to be n. Now in Dorher's paper, they have suggested to choose the parameter to be between 1 and n. But we have modified it here in our case to take the parameter to be the maximum, because we are searching for a error vector with a weight with minimum and also satisfying the syndrome. But if we choose it randomly, it may have a possibility to choose the weight less than the actual weight that should be. So whenever we do this algorithm with a minimum, with a lesser weight than that minimum we are searching for, we're searching for a wrong weight which should be minimized and also satisfy syndrome. So the whole theory fails. We have suggested to take the parameter to be maximum, that is all one in this case. Then we have implemented our algorithm in QASM simulator of IBM quantum experience. Obviously, we cannot implement it in a real quantum computer because there is no class error correcting code has been involved. And we have implemented it for 633 code and given syndromes as 011, then we get the error vector this. And for the syndrome 001, we get the error vector this. And if we match, we also see that the probability is 0.80858215. So the probability is greater than 0.5. And if we actually look for the Cossack table of the 633 coder, these are the actual error vectors that has been happened for this syndrome. Now we come to the point where the 633 coder cannot detect and say which is the error vector that has been happened, and that is due to this, the Hamming weight of the 633 is 3. That is, this cannot detect and correct with the errors that has been occurred for more than one number of bits. So here these 3 occurred for syndrome 111. Now in any of these 3 can be the error that has been occurred, but we don't know which one occurred because all of them has almost equal number of occurrences, and obviously the nature is probabilistic, so it is non-deterministic which one has occurred, because out of the others these 3 only has higher probabilities, and that also gives us the verification of the minimum Hamming weight dependency of the linear block code. And with that, I have also want to express the domain of utility of our algorithm. That is, our algorithm only gives a quadratic speed up, which is helpful for higher number of bits, because in lower number of bits, classical process, which is 2 to the power n 7 to the power 2 to the power 4, is helpful, because that is the quantum case exceeds the time complexity in lower cases. But as we increase the number of bits, the time complexity is exponential on the number of bits. So obviously, as we increase number of bits, the classical process gets exhausting, and the quantum process gives us a visible speed up in the searching process. And I'll end with a quantum syndrome detection technique. That is, if we apply this operator on the initial preparation of, say, k bits on this, out of this n bits, k bits are message bit, and the rest of n minus k bits are zero MCLR bits, then if we apply this operator here, we'll get a code word. And the code word will be modified by some bit flips by this noisy channel. Here we'll get erroneous vector, and if we apply this operator's dagger here in the answer bits, we get the symbol. So ultimately, we have proposed a complete quantum syndrome detection technique. That is, we have encoded the message bit into a linear block code using the operator UF. Then we have operator UF tagger on the erroneous vector to get a syndrome in the answer bits. And then we did a decoding process based on or inspired by the Grover's process and Dorhal algorithm to give us a quadratic speed up over the classical searching process. And we showed the domain of utility for this is for higher number of bits, where the classical search process is exponential on the number of bits of the code word, and that gets exhausting. And then the quantum syndrome decoding algorithm comes into play, which gives us a better quadratic speed ups and rescued us from the exhausting search process. Thank you.